So welcome back. And yesterday, we started to discuss the particle hole formalism and with selected examples, but we didn't look at a diagrammatic representation. We will continue with this today. And the whole idea then is to migrate everything which we are doing now into our first real many-body method, which is what we have been calling full configuration interaction theory, which simply means that we are setting up a matrix, which we diagonalize. This matrix is called the Hamiltonian matrix. But I wanted to go through this particle hole formalism because that gives us a very handy way to represent states and also to interpret the type of correlations which we bake in. And the type of correlations which we bake in are often loosely called particle hole excitations or particle hole correlations. And we will try to guide you through why this becomes a useful language to use when you want to interpret physical results. Because keep in mind again that we don't have the exact solution. And that means that we have to make approximations. And then these approximations, the way we describe the system, gives us a way to interpret the results. And essentially, this is what science is about, to have good tools which allow you to interpret the results in a meaningful way. And then, obviously, to be able to repeat experiments under controlled situations so that everything matches what you had developed theoretically. So I also wanted to quickly remind you of the exercises. So one of the things which I did in the exercises from last week is to add in the answers to exercise 1, which is a continuation of this Lipkin model. And then the second part, exercise 2 here, is something which I will roughly go through in the lecture here today. So you will, in a certain sense, have the solution to the exercises, both from the lecture notes and also from this set of answers here, which detail the different derivations with angular momentum, representation of the Hamiltonian, the commutation rules, the fact that angular momentum shares the same eigenstates as the Hamiltonian, etc., etc. Okay, so I'm going to switch back to the whiteboard rather quickly. And let's use that one. So the thing which we did yesterday was to introduce a notation where we now divide, obviously, the whole single particle space in terms of states below the Fermi level, which we loosely call for Hall states, and states above the Fermi level. These are single particle states. Then, by filling them up, we use these single particle states to make an ansatz for a many-body state. So let's quickly just remind ourselves what we did, and we will have a set of states, and then continue up to an n minus 1, and then we have an n plus 1. So these are the particles which we are having in the system. That depends also the density of the system, because number of particles divided by the volume defines the density. So we often call this also a density-related variable. And then, since we are mainly stuck with fermions, we define a Fermi level, and then we have additional states, n plus 1, and this continues, and then there is a state here. And in principle, this should go to infinity, but we stop at a state n. So you could have thousands of such states. Ideally, you would like to have few, because the dimensionality of the system, the many-body system, explodes quickly. Now, in here, we have a state I. We're going to put a label A. So what we did then was to label states like I, J, K, L as states below the Fermi level. And then we have A, B, C, something. These are states above the Fermi level. And then we have a generic single particle state, which we label with the letters P, Q, K, P, Q, R, S, etc. Now, when we have more than 4 or 5 particles, we will often put a subscript here. So we will have I1, I2, I3, etc., because we are quickly running out of letters. But since mostly now with the particle hole formalism, we will mainly deal with 2-particle, 2-hole, 3-particle, 3-hole excitations, and operators of the type of 1-body, 2-body, perhaps a 3-body, then this combination of letters can be sufficient. But if not, I will put a subscript on, let's say, the A's here. And so these letters will then refer to states above the Fermi level. So this is a kind of notation which we will use throughout the semester. And the total number of configuration then, just to quickly remind you that, because when we are entering the world of configuration interaction theory, it's actually us calculating the expectation value or transition probabilities from one Slater determinant or one state to another state. So the total number of configurations is then given by a combinatorial factor, configurations, and that is typically given by n of n. So uppercase n is the single particle states, the last one, and this is n divided by n minus n factorial, and then we have n factorial, and this grows quickly. Now, the assumption is that n is larger or equal than the uppercase letter n. What we also defined then was to rewrite all the so-called Slater determinants or the ansatzes for the wave function. So remember now we have a Hamiltonian H0, which is an eigen, which has as eigenstates these Slater determinants. So this is given by some epsilon I or phi of I. What we did then was to relabel these spaces and reorder it in terms of particle hole states. So you could make a list, your preferred list, where you simply distribute the particles. So what we typically would have here would be an ansatz for the ground state where we fill in everything here. So this would be typically our ground state ansatz. Now, if we fill in everything there, then this can define an ansatz for the ground state. And then we can scatter these particles into the other states here, which are normally called particle states or unoccupied states. And then we create additional Slater determinants. What we did yesterday was to introduce a reordering of these states so that we have a pH, which is now a particle hole configuration. So we have 0 particle, 0 hole, and that is normally given by the ground state ansatz. We have a new block of states, 1 particle, 1 hole. If you now look at this figure here, this is the block which contains all the ways you can excite these guys here up here. And if n is an infinitely large number, then you have an infinity of 1 particle, 1 hole excitations. So in principle, these blocks, as we call them, they are infinite, but we will obviously always make a truncation here. So we have this, and this runs up all to n particle, n hole excitations. So n particle, n hole, that means that if I now have 10 particles here, I can boost up all the 10 particles up here. And then I will have a 10 particle, 10 hole excitation. That sounds pretty logic, right? If I have 4 particles, I can only make 4 particle, 4 hole excitations. So typically the number of states below the Fermi level, these states here, n, this is normally a number. N is normally, the normal case, much, much smaller than n. Okay, so what we did then was to define the states in the following way. So we have a 1 particle, 1 hole state, which we wrote like this. So this is us simply having the excitation of a particle into state A. We have the removal of a particle in a single particle state I, acting on the true vacuum state. So this obviously assumes that I is included in phi 0, and A obviously is not included in phi 0. So this is an example of a 1 particle, 1 hole state. And going back to that image which you saw here, this means that we kick this out of state I and up to that state I. And that is a new way to organize your single particle states. And you would call that a new configuration. So every one of these guys here, which you see in here, and so on, they represent one of these possible configurations. The way you just distribute these objects in n, little n slots. Okay. Now, with that kind of organization, what we did yesterday was then to rewrite. Suppose now we want the ground state of the system. This is the exact ground state. And since we now have an orthogonal basis, so this basis which we have of states, this is an O and B. It's an orthogonal and normalized basis. So this state can then be expanded in terms of all these possible particle hole excitations. So this is a more compact notation where we have a state now which represents all the possible particle hole excitations we can make. I'm going to put a C0 here, which is just a zero particle, zero hole. So that's the first coefficient. And then we have the next one, which is now a one particle, one hole case. And then we have these unknown coefficients multiplied with this state. This is again, as we said yesterday, AI acting on the vacuum state. So you could actually rewrite this one as an operator. So if you call this for an operator A of I and A, then you could write this in a more compact form. You have an unknown coefficient, which you will get from the diagonalization. And then you have the operator now, which then creates the specific state. And this continues all the way up to n particle, n hole excitations. So I would have a Cij, AB, and then I have a phi, ij, AB. And this is again an AI, AB, AJ, AI, acting on a true vacuum state. And then finally, this goes all the way up to, and I'm simply just writing this as n particle, n hole excitations. And we wrote that down yesterday. Now, what we did also yesterday was to redefine the contractions using the old-fashioned annihilation operators and creation operators. So let's quickly remind ourselves about that. And then we are going to set up some examples and also look at how we can write the two-body interaction with respect to the new vacuum. So what we did was to redefine these contractions, AP, AQ dagger, that is equal to delta PQ if P and Q, both of them are above the Fermi level. And then I had a new one, which previously was actually when we used the true vacuum, that was exactly equal to 0. But now we're going to put it different from 0 if P and Q, both of them are below the Fermi level. Because now we have redefined the vacuum. And we saw that immediately when we calculated yesterday an expectation value of this type. So this is the same as this contraction, but now with respect to the new vacuum. So if you look at what we have here, this is the same. This, what you see here, is the same as this quantity. Now, clearly, if Q and P, if they are included in phi 0, that means that we move away a particle in phi 0, and then we create it again. And this is only possible if P and Q are the same. The other contractions, AP dagger, AQ, and AQ dagger, AP, doesn't matter which order they take, these are equal to 0. Now, one thing which we also did yesterday was to derive the one-body operator, and we could rewrite that one where the sum now runs over all the possible single particle states. And we have an integral P of H0 of Q. So this is an integral. And if these are eigenstates of H0, then this simplifies to a constant. And then the double sum reduces to a single sum, because then we would have an orthogonal single particle basis. But now we're just going to leave it like that. So we just keep it as general as possible, because we could think of having other types of operators over one body type, which may not have this basis as an eigenbasis. So that's fully possible. Just to give you an example, if you only have kinetic energy and you use a harmonic oscillator, the harmonic oscillator is not an eigenbasis of the kinetic energy only. The harmonic oscillator basis is the eigenbasis of kinetic energy plus the harmonic oscillator potential. So that means that if I were to calculate the expectation value of H0 for the kinetic energy, and I use the harmonic oscillator, that would not be diagonal in P and Q. So we can just keep this in a very general sense, because we could now think of no external potential which confines our particles. And then H0 would often reduce then to just kinetic energy. So what we could do then was to rewrite this one in terms of normal ordered with respect to the new vacuum, with respect to phi 0. And then there is an additional term, plus, which is now the reference energy. And this epsilon reference is an uppercase letter. This quantity here, so this is a plus, and this quantity is then equal to the sum over I less than the Fermi level of I of H0 of I, like that. And then clearly the P and Q have to be equal to I. So the thing which we're going to do now is actually to look at the two-body interaction. And yeah.
Is this a standard convention or something that differs from textbook to textbook?
So this notation which you see here is a notation which I picked from the textbook by Shavit and Bartlett. If you go into other textbooks, you may see just a column, for instance, just to indicate that this is now normal ordered with respect to a given vacuum. If you don't see a symbol like this one in this course, then this is just normal ordered with respect to plain emptiness, just the true vacuum, or whatever that is. Okay?
I believe I saw the contractions.
The contraction here is this one? No, because the contraction is then simply this quantity here. So if we have the true vacuum, this is already normal ordered. And then for the true vacuum, this would definitely be, unless this state, if it doesn't contain Q and P, then this is automatically zero. Now, what we're going to do now is to rewrite the two-body operator, and that's part of one of the exercises. So let's just take the H of I, and the way we wrote it with a normal ordering with respect to the vacuum, not a reference state. So we have an integral PQ V of RS. So we can use anti-symmetrized matrix elements, or we can have just the different integrals, the so-called direct or the exchange term. So if you see 1/4 here, then we are looking at anti-symmetrized matrix element. Just let me quickly remind you of that, because that is PQ of V of RS minus, and then I have QP of V and R and S. And then we have the multiplied with the creation and annihilation operators. Now, a simple way to actually look at this, because this is now normal ordered with respect to the vacuum state 0. But now we want to have it normal ordered with respect to the new vacuum. So what we are going to do now is to rewrite this operator by using Wick's theorem and look at the different contractions which we can have. So let's now do that. And I'm going to, for simplicity, just to keep this term here. So if I use Wick's theorem on this chain of operators, then I'm going to have this operators normal ordered with respect. So in the lecture notes, you will find the same calculation, but where I introduce the operators which we discussed yesterday, the particle hole operators. So this is now normal ordered with respect to pi 0. And you will see that this is the case because if you are now going to take the vacuum to vacuum expectation value of this quantity here, then you have to plug in phi 0 and phi 0 here. And when you then use Wick's theorem on that, when these operators now have been normalized to the normal order with respect to the true vacuum, what we have then is that we need to set up a normal order product with respect to the new vacuum. So I will have an AP dagger, AQ dagger, AS, AR. So I can have this contraction. So this is the sum of all one pair contractions. And then I leave the rest uncontracted. So this is just an application of Wick's theorem. Now, in this specific case, I need to have delta Q and S, and they have to both, so Q and S have to be below the Fermi level. So we can just write them like this. So less than F. Then there is a new term where I take AP dagger, AQ, and then I have AS and AR, and I have this contraction. Now this one gives me minus because I have to interchange these two operators so they can be contracted properly. And that gives us minus delta Q of R. And both Q and R have to be smaller than the Fermi level. Then I have further terms. So because I'm now going to set up all the possible contractions which we can have. APQ dagger, AS, AR. And we will now have a contraction like this one. And that is just going to give us, since I also have to interchange these two operators, that will also give me a minus sign. It will have a delta Q of R. No, it's delta Q, no, P, that's P, sorry. And this is delta Q of R. And then I have another term, and they obviously have to be below the Fermi level. So I would have gotten these terms if I were to use Wick's theorem on the expectation value of this quantity here with respect to the new vacuum. So then what I'm getting next is an A dagger, AQ, AS, AR. So here I would have a contraction like this one. Now I then have to permute AR with AS and then AS with AQ. So that gives me a plus sign. And this one simply gives me a delta P of R. And obviously P of R in all these cases, all these Kronecker deltas, they tell us that the states which we pick out, they have to be below the Fermi level. Then finally, what I have now is the terms with two contractions. So I have the normal order product. This is just Wick's theorem again. An AQ dagger, AS. And then I can have this contraction of AR. And then the only other possibility, which gives us something which is non-zero, is the cross term. And that's going to give rise to a minus sign. So I will have this one and that one. So the crossing lines here, they normally indicate that we'll have a minus sign. So this will give us delta Q of S and delta P of R. And they all have to be below the Fermi level. And here I will get delta Q of R and delta P of S, and they all have to be below the Fermi level again. Now, if I go back to the operator, what I'm going to get now is the following. So I will, for the operator, so H of I with respect to the new vacuum is going to be given by 1 over 4, and then I have a free sum over PQRS, and then I have a P, so these are all possible states which I can have. And this is then, has an anti-symmetrized matrix elements, and it's multiplied with the normal order product with respect to the new vacuum. Often we skip these curly brackets. That's pretty common to do that. Now, if I now look at the next term, I will have a term which has a one-body type of operator. If you look more closely at that one. So this is going to give me AP, AR, AP, AQ, AR. Now, these are dummy variables. So I can always, in the summation, I can always change the values. So remember that you have a quadruple sum here. So the Kronecker delta is now going to reduce the quadruple sum to a double sum. And I'm going to have, due to the anti-symmetric matrix elements, I'm going to have 1, 2, 3, 4 contributions. They are going to give, due to the anti-symmetrized matrix elements, I'm going to get 4 terms which are the same, and that will take away the factor of 1 over 4. So when you collect all these terms, you're going to get a term here which has just a sum over P and Q. But then pay attention now that if you look at the forms here, one of these guys here has to be a state below the Fermi level. So that means that what I'm going to get now is that one of the summation disappears due to the Kronecker delta, and I will have a matrix element which is P of I, of V, and Q of I, anti-symmetrized, but that will have a one-body operator, AP dagger, AQ, and the final term is a term where the quadruple sum is reduced to a double sum, and you have 2 elements here, this one and that one, and you have a factor 1 over 4, so that gives us a half, and that's just going to be a sum over I and J, IJ, V of IJ. And this is something which we also calculated earlier, which was the expectation value of H of I for the vacuum to vacuum state, or the reference state to the reference state. So if we now reorganize a little bit what we have, we are going to rewrite H in terms of a term which I'm going to call E0 reference. That's the full Hamiltonian, plus an operator here, which I'm going to call F of n, which is going to be a one-body operator, and then a V of n. So let's take a closer look at what this is. So this E0 ref, this is going to give us a compact notation. And this is normally something which we can pre-calculate. This is the same as phi 0 of the Hamiltonian, the ansatz which we have chosen. And if you have a given basis, this is something which we can calculate. And you remember that that one is given by epsilon 0 ref, which is simply the sum over all the single particle energies up to the Fermi level. So I have an I, and then I have H0 of I, plus this term, which we have here, this one. And that term gives us now, plus 1/2. And this is something which we calculated really from the very beginning of the semester. So I have IJ, V, IJ, anti-symmetrized. This is the reference energy. And normally now when we are going to calculate the eigenstates of systems, we are going to interpret them in terms of the reference energies plus something. So if you have an ansatz for the ground state, the assumption then is often that this is something which can be calculated. Okay. Now, what falls out automatically here is that you have the only two-body term. That means two pairs of contraction and annihilation operators is given by this one. So if I want to interpret this term here as a two-body interaction, this falls out automatically. So V of n is then just 1 over 4, and then I have a sum PQ RS, and then I have the integral PQ V of RS, and then I have AP dagger, AQ, AS, and AR. So that is set. Now, if we now look at what remains here, I'm going to define this one in terms of a sum over P and Q. There is an integral, which I'm going to call with a function little f and Q. And then we are going to indicate that this is, at a certain point, I'm going to skip both the anti-symmetrization sign and the curly brackets for simplicity. But now I will try to keep them. But then when we move on next week and so on, if you see a factor of 1 over 4 here, like this one, then that normally means that you have anti-symmetrized matrix elements. And it's pretty common to just drop the AS. And since we always will work with a reference state, it's common also to drop these curly brackets. Now, this guy here is then equal to AP, AQ. And now we have to fill in the elements which we have here. So if we look back, you saw that there's a term like that. So that is a one-body operator. And then if I go back a little bit more, and I look at the one-body term, which I had before, then there is an additional term, which is of the one-body type. Now, this brings in a very, very interesting connection, because it allows us to define this as a mean field term. And when we are going to do Hartree-Fock theory or density functional theory, these terms here are going to play a very important role. So, but let's now write up this term, this little f here. So this little f, PQ, or little f now, is the original one where we had the one-body operator, and this could just be kinetic energy. It doesn't need to be an external confining potential. So if you have an isolated system, like a nucleus, yeah? Oh, sorry, it should be Q here. Thanks, yeah. And then we have the next term, which now contains a sum over I less than F. And there we have the P of I, of V, of Q of I, and this is anti-symmetrized. Now, so what is happening here? When you have normal order this, you're bringing in a natural way, a very interesting contribution. And the interesting contribution is actually this one. So how can you think of that? So suppose now that you have a medium here, and if you're now doing, let's say, nuclear physics, just to give you an example. So this could be oxygen 16, which has 8 protons and 8 neutrons. And in your case then, if we look at oxygen 16, you have, in nuclear physics, it's common to use what's called the harmonic oscillator as a basis, as a kind of computational basis. So you would have a 0p orbit and a 0s orbit with the harmonic oscillator, and you can place 2 protons here, and same with neutrons, like this. And then you can place 6 here, and this is the same as you would have in atomic physics. And then you would have the Fermi level here, and then you would have many more single particle states here. Now, if you now look at this summation I here, this summation runs over all these single particle states. So suppose now that there is a lonely proton which comes in here in a state P. So not only for proton, it could be a neutron as well. And then it sees these guys here. So what is happening now, if P is given by kinetic energy only here, then when it is now approaching this nucleus, it sees a mean field, which is set up by all the other particles present here. Now, this guy here could now be absorbed by it. And then I would get the 17 fluorine, which has 9 protons and 8 neutrons. Or it could just scatter away. And actually now I use Q as the incoming state. And then I should put a P here. So this particle comes in, it sees an effective field, which is being set up by all the bystanding particles, which are down here. So that means that its motion gets modified by the perturbation or interaction, which is set up by this medium. So the guy which you see here then represents what we will call a mean field contribution. So that means that the bystanding particles, they are setting up a mean field. And that changes the motion of the object. So previously, when we didn't think of a medium at all, we just had the true vacuum, then we were pretty happy with just calculating this quantity. But now with a vacuum, we can actually give a nice interpretation in terms of the motion of a particle being modified by the particles which define the medium. So this is actually the first stepping stone towards mean field methods like Hartree-Fock theory and density functional theory. Okay? So I'm going to repeat these things, but this is just to give you a kind of a conceptual hook to put everything on. So what we have now is a Hamiltonian, which we now can set up like this. So let's use this to calculate. And let's see what happens. Because there are some, with this more compact formalism, there are expressions which we just can zero out immediately. And you can develop a kind of immediate, insight on why this happens. So let's take a look at a specific expectation value, phi 0 of H, and then you have this one particle, one whole state. And the question then is, what is this going to give us? So if I think back a little bit, this belongs to all the possible one particle. It's just an example of all the possible one particle, one whole excitations I can make. So what I'm going to have then is obviously, if we break everything down, so we will have the first term, which is epsilon E ref is a constant with phi I A. So keep in mind now that this is a constant. What should we get then? We don't need to calculate even. So this is a constant, so you can just pull it out. But then you're taking the overlap between this state and that state. And this is an orthogonal basis. So this is 0. So you can just look at the expression and say this has to be 0 because this is just a constant. Then we take the next term and let's look at that one. So we have a phi 0, and then we have the term here, which is a sum of a P and Q. And now we are putting in this operator, this new operator, which then gives us a new integral. And now I have my operators, and I'm skipping the curly brackets just to avoid notational confusion here. And then I have my AI acting on phi 0, like that. So when we are looking at the contractions here, since these are normal ordered operators with respect to the new vacuum, the only contractions which will survive here are contractions of this type and that one. All the other ones are zero. Because if I try now to contract this one with that one, that is by obvious definition zeros. This and that one is zero. Now, if I try to do this contraction here, that's a contraction between the same normal order product, and that is by definition equal to zero. And also, this has to be zero because this is a particle state, and this is a state below the Fermi level. So A and I are by definition always equal to zero. So that means that if I take this contraction and that one, that gives me automatically zero. Okay, so this is the only guy which survives. So that leads to, what that leads to is actually a final expression where the double sum is now reduced to just one contribution. So P is equal to I. So that means that in this specific case, the expectation value of phi 0 of this operator Fn, which is the one-body operator, that is equal to I, and then this new integral, this new operator, which then defines a new integral. And that object is, if we now go back, that is the same as this type, this guy here with I and A. And then I have here I, and then I have to change to J here and J, and I have A here. So this is just a simple expression. That means that all the matrix elements, which now we are going to construct later when we do full configuration interaction theory, which link the ground state with this block here, they are just equal to this quantity here. Now, when we do Hartree-Fock theory, one of the standard choices is to set up a recipe which put this one exactly equal to zero. So you will see later that Hartree-Fock is going to correspond to a unitary transformation of your Hamiltonian matrix, which just zeroes out these elements. So Hartree-Fock comes after we have discussed full configuration interaction theory, because Hartree-Fock becomes an approximation to full configuration interaction theory. Okay, so that was, and then we have the final case. And here is a kind of intuitive way by which we can see that this contribution here has to be exactly equal to zero. So this is now the expectation value or the transition probability of the two-body operator acting on this one particle, one whole state. So in principle, when we now break it down, so I'm not going to write up everything. I'm not going to put up the quadruple sum, the integral, and so on. I'm just going to look at the operators. So I have AP, AQ, AS, AR, and then I have my A, and AI. And this is essentially what we are calculating now. So if you look at that one, without you having done any calculation, what should it be? So if you now look, I want to give a small hint. If you look at this as V of n acting on phi 0, what that can produce is the following. It can produce something which is proportional with phi 0. It can produce something but which is proportional with a two-particle state. But it's not going to give us a non-zero contribution, which is a two-particle state, a one-particle, one-hole excitation. Yeah? Yeah. Because this state which you produce here, this one, will then have to match a one-particle, one-hole state. And there are some constants which you multiply this with when you act with the Hamiltonian. So you will produce this one, but then you will produce a two-particle, two-hole excitation. And then if you want to match that with this one, these states are orthogonal, so that is automatically 0. And you can see that from the contraction rules, because what you end up with is that you will have a pair of operators within the same operator, which are not contracted with an operator from outside that operator. So it means that this one is a viable contraction, and that means that this one could also be a viable contraction, but then this guy and that guy are left uncontracted because they are within the same operator. And if you use Wick's general theorem, this is going now to only include contractions between sets of normal ordered operators. These are the only ones which give us a non-zero result. And you see that immediately, because if you do that, then what you're left with then is, so suppose you contract these two guys, which we have here, then you're left with that one and that one. That is going to create a state here, which when it acts on this one, it would create a typically one particle, one hole pair, because that's the only non-zero thing it could compute. And then you are going to calculate with that one, and that's going to give you 0. So what typically this one does is that either it just gives you something which is proportional to the ground state, but it can also give you something which is a two-particle, two-hole excitation. And if that is the case, then you have orthogonal states, and then this is automatically 0. So this term here is something which we can put to 0 only. So that means that phi 0 of h of the Hamiltonian over one body over one particle, one hole excitation is given by this integral I of f of a. So after the break, we're going to look at some other examples. Now, the thing which is nice with this kind of way of thinking is that you're actually acting with an operator on a state. So this operator, which is a two-body operator, can actually take away a one particle, one hole point, it can delete it, but then it creates a new one. So it will always create something which does not match the side here. But if you do the contractions, so I'm just bringing this in because this is some kind of intuition which you can develop with time after you played around with setting up the contractions in a more standard, straightforward way. Okay, so let's continue a little bit with more examples, selected one transition matrix element. Let's now look at the couple. And in that case, what we're going to do now is to set up the operators. So phi 0, and we take H, and then we have a two-particle, two-hole state. Recording here. Okay, so let's continue with the calculation of this quantity. So we would obviously have the first term, which is phi 0, and then we have the reference energy, this E ref, and then we have a phi I j a b, and this has to, since epsilon 0 ref is a constant, then this is simply equal to 0, because this is the same as just a constant being put outside, and then we have a phi 0, and then we have a phi ij ab, and that has to be equal to 0, because these are two different states, and it's an orthogonal basis which we are setting up. Okay, so that piece is pretty easy. Let's now take the next piece here and look at phi 0, and then we have the operator Fn. And now we are just going to run through the calculation. But at the same time, I'm going to try to develop your intuition so that you can see immediately that this is going to be equal to 0. And to develop the intuition, if you now look at the operation of f of n of phi 0, if we look at that one, that is going to give us something which is a constant multiplied with a one particle, one whole state. Because this is an operator which goes like AP dagger, AQ. So it can produce phi 0 by just annihilating one particle, which is in phi 0, and just recreating it back. So it could create a constant times phi 0, but then it could also create a state like phi I here. It could create a particle whole state. So these are the two possibilities of the action of that operator. But then when you look at the terms which you have, this is an operator which now has two particles, two holes. So suppose now that if you now look at this, suppose then that you are creating a one particle, one hole state, then you will have an overlap between this state, and then you have the state here, and now I'm going to put different indices, K and L and C and D. And this is a two particle, two hole state with a different single particle state and a one particle, one hole. So this has to be equal to 0. So you can think in a kind of physical way, a pseudo-physical way, where you can think of these operators creating some new intermediate state. But since this is a one-body operator which you have, it can at most create a one particle, one hole excitation. And that means that it creates a state which is a one particle, one hole state times some constant in a sum of constants. And then you're trying to take the overlap between actually two states which are orthogonal to each other. So that's automatically 0. But let's go through the calculations, because then you will see this immediately, okay? So let's do the mathematics. Sometimes it takes time to develop this kind of intuition. And what we have now is a sum over P and Q. We have this integral P of F of Q here. And then we are now setting up the states. So we have phi 0, the new vacuum. Then we have the operator AP, AQ. And this runs over all possible single particle states. But now we have states which are well defined. So A and B are particle states, and J and I are whole states. And these are definitely not the same. So these are different. And if you now look at the contractions here, what we could have as possible contractions is perhaps this one going to that. Now, if I take a contraction like this one to that one, that is by definition 0. So that's obviously void of interest. But the only one which would be non-zero here would be if I now take this one to that. Alternatively, I could let this one go over there. But what you see now is that you have two operators, one creation and annihilation operator, which is not acted upon by the state. No, sorry, not the state, but by the operator. So it means that since these, and if we follow Wick's generalized theorem, we will have two operators which are left uncontracted in a generalized stream of normal ordered operators. So if we now leave this one as it stands, so the kind of contraction like this one is 0, if we want to do that. And we see that immediately because B is not the same as I. So you will be left with two operators now, like AB dagger and AI, which in principle could create a one particle, one whole state, but then you have a 0 particle, 0 whole state. So from these equations, you see that this one is equal to 0. So then the only thing which remains is the two-body operator. So let's look at that final term here. And in this particular case, what we are going to have is a sum of a PQ Rs, we have the two-body matrix elements, or integrals, to be more precise. And this is multiplied with, and then I have these expectation values, which I have to calculate, AP, AQ dagger, AS, AR. And now I have AA, AB, AJ, AI acting on the true vacuum state. So now I have actually sets of operators which can be contracted and which hopefully will give us something which is different from zero. So I'm going to rewrite just the operators on the next page. Yeah. Oh, that is a B. That's a B. Yeah, that's a B. Sorry. It's my handwriting, bad handwriting. So let me bring this over to the next page. And as we always do, we are just going to single out the contractions only. So we leave out phi 0 and phi 0. So it's understood that this is something which is acting on a specific state. So let's just write them down here. So we have an AP. So these are general states, which can be both above or below the Fermi level. But for the state which we are acting on, we have specified these to be two whole states and two particle states. So it means that the contractions which we can do are actually limited. So we can make this contraction here and that contraction. So that will give us a delta S of B and then a delta R of A. Then I have the whole states. So where Q can be contracted with J and P can be contracted with I. So we have a delta I P and a delta Q of J. This is going to give me a matrix element, or better, an integral, which runs like Aij, V, and AB, anti-symmetrized. So that is one of the contractions which I'm getting. But I can now interchange. So I can look, so this is the first one. And let's look at the second one. So the second one could now be us just keeping these two guys here, like that. But now I interchange S and R. So I can let R go to B and S go to A. That's going to give me a minus sign because I have to interchange the operators. So I will get an I and J and V, and this is B and A, anti-symmetrized. But since I'm using anti-symmetrized matrix elements, this is simply going to be IJ, V, AB, anti-symmetrized. And now you see that I can get two more terms. So the additional two terms is obviously me keeping this fixed, but now letting the two here be changed so that P goes to J and Q goes to I. That will give me a minus sign. And then I can have this, this ordering for the particle states. And I could then keep this one with P going to J and Q going to I. So there will be two more types of contractions which are non-zero. So what I'm going to get then is two more terms. So let's just write it down here. I'm just going to write down the results. And there will be one term which is now going to be JIVBA, anti-symmetrized, which is again the same as IJ, since I'm using these anti-symmetrized matrix elements. And then finally, I'm going to have a term which is actually going to be JI of VAB. It will have a minus sign because I have to permute an odd number of times the operators, but this is the same as IJ, V, and A and B, anti-symmetrized. So I have four terms. I have a factor of 1/4. So that means that this specific contribution from phi 0 of H of phi of ij AB, that is equal to this specific integral of E, and there's only one term. Now, some weeks ago, actually 2 weeks ago, we had an exercise where we derived the Condon-Slater rules. And you could have seen this from using the Condon-Slater rules. Because then what we found in that exercise is that if the Ket side differs by 2 single particle states from the Bra side, then this is the contribution you should get. So if you go back to the exercises in week 36, when we derived the Condon-Slater rules, we looked at the transition elements when we had the same Slater determinant on the Bra and Ket side, a Slater determinant which differed by 1 single particle state, either with a 1-body or 2-body interaction. And then we had the case where we had a Slater determinant which differed by 2 single particle states, which is the case here, because we have 2 different states which are now A and B with respect to phi 0. So in principle, we could have used the Slater-Condon rules. This is just another way of calculating the same result, which we did in week 36, where we looked at the integrals using the coordinate space degrees of freedom plus the spin degrees of freedom. But you could have derived this using second quantization. That means that if I now take a new example, you should be able now, if you take what you did in that exercise in that week, if you now look at the free particle case, and I have H, and I have a free particle free hole excitation, JK, and then A, B, C. And this guy here is at most a 2-body operator, like we had in that exercise. What should we get then? So now we have 3 single particle states which differ in the Ket side compared to the Bra side. So if you spool back and reboot your memories and think back to the exercises in week 36 and the Condon-Slater rules, because you could actually now set this one to a very simple number. It's actually the roundest number you can think of, 0. And you would see that immediately, because in this case, you would have free particle, free creation operators and free annihilation operators. And there's no way you can match a 2-body interaction and produce a 0 particle, 0 hole excitation. So that means that there will always be a state here which is uncontracted. So the action of this one can produce at most, at the lowest level, a 1 particle, 1 hole excitation. So this one acting on here can give a 1 particle, 1 hole excitation, but then you have a 0 particle, 0 hole excitation, and that's automatically 0. So the formalism becomes very powerful, because you can just say that, hey, I see immediately here from the operators. So if you were to have an additional operator here, so for that specific example, you would also have an AC, and then there would be an A. So in here, there would be an AK. And this set of operators would actually not be contracted with the operator here. So it means that you would be left with something which could be a 1 particle, 1 hole state. And that doesn't match the 0 particle, 0 hole state. So the very, how to say, nice ways of thinking of the action of a Hamiltonian or an operator on a given state. Okay, now this becomes a little bit more interesting for us. Now, and the reason for that is that I'm going now to set up a diagram where we look at different types of contributions to what is going to be a Hamiltonian matrix. So I'm going to use this as an intermediate step before we do the full configuration interaction equation. Intermediate step. And now you will see the benefit of reorganizing everything in terms of this one particle, one hole, two particle, two hole, three particle, three hole excitations, etc. Intermediate step before FCI. So I like to use this example here in order for you guys to develop an intuition for what we are doing. So keep again now in mind that what we did is that any state, but here we are looking at the ground state, but this you can do this for any state, is now given by this sum over particle hole excitations. And you have a CH of P, and then you have this phi H of P. This is the way you are going to expand your specific state. Okay? So let's think of this as us building up a Hamiltonian matrix. So what we're going to look at first is now the action. So we are going to have H acting on psi 0. This is what we want, and this is going to be equal to E0 times phi 0. So we don't know that one, but we are expanding this one in the basis of these single particle states. So what we are doing then is that this is going to be given by some Hamiltonian, which is now acting H on the CHP of phi HP. And this is equal to E0. And then we have the same sum PH and CHP of phi HP. Okay? So what we are going to do then is obviously to calculate this problem here. So we're going to have psi of H, psi 0. And this is obviously going to be given by E times psi 0 and psi 0. And then we want to optimize this problem. So we have what's called the Rayleigh-Riggs coefficient. So what we end up with is that E0 is ideally given now by psi 0 of H, psi 0, divided by this norm here, if it hasn't been normalized. So let's now do one thing. What we are going to do now is simply to look at the different components which you get from this expansion when you multiply them in. Okay? So let's now look at a row here where we have phi 0. And this is now being multiplied with the Hamiltonian with psi 0. So this gives us now blocks. I'm going to write this in terms of blocks. In terms of blocks. And blocks are particle hole blocks. So when I do this now, there will be one block, which is phi 0 of H0 of phi 0. Okay? Then there is a new block, and we know the matrix element. This is what we called E0 ref. I'm going to set this up in this specific way. So this is the first block. And if this state, phi 0, if this is a non-degenerate state, there's only one, the one and only, then this is just a number, right? But then I have the particle hole block, the one particle, one hole. So I'm writing this in a generic way, but this is a 1p, 1h block, which links the ground state ansatz with a one particle, one hole excitation. And what we found is that this is given by this specific integral, which we can calculate. The next block is a phi 0 of H, and I'm actually running a little bit out of space here because this is going to continue. Now this we calculated, and this is given by this specific integral, AB, anti-symmetrized. So this is a two-particle, two-hole block. And all the elements which we have in that specific block, they are of this form. Now, keep in mind that we have many such states. So if I have 100 states, and I have only one state here, this will contain 100 elements. If I have 10,000 two-particle, two-hole state, and only one zero-particle, zero-hole state, this will then be a vector of length 10,000. That makes sense? So that's why I call them for blocks. Now, why is this interesting? Now, it is going to get interesting now because if I continue, so if we now move on to the next side, and then you write free particle, free hole, and this can now continue all the way up to n particle, n hole. And in this case, I have phi 0, and then it's the Hamiltonian, and then I have phi I, j, k, and then A, B, C. This is exactly equal to 0. Okay? And all the other ones have to be 0. Because here we have 3 states which differ. Then we have 4 states which differ when I go to 4 particle, 4 hole. And then at the end, I have n particle, n hole states which differ from the phi 0 state. So it means if I use the Condon-Slater rules, these have all to be 0. So when you now set it up, you could think of this as one long row. Now what I can do then is to think of this as us having multiplied with phi 0. Okay? Then in the next case, I have phi IA, the one particle, one hole case. Then I'm just setting up 2 particle, 2 hole, free particle, free hole, etc. down to n particle, n hole here. Now, in this specific case, this one is going to be A of F of I. This element here, and now I'm going to do something because this will contain, in general, a phi JB of H of phi IA. And this is not necessarily 0. Okay? So this is something because we have a 1 particle, 1 hole state and a 1 particle, 1 hole state. Actually, in the first midterm and also in one of the exercises, you're going to calculate this type of elements. And you will see that they are not necessarily equal to 0. So what I'm going to do now is actually to set up elements which are non-zero. I'm going to mark them with a cross. Does that sound okay? So that means that if I now go down again here and multiply with 2 particle, 2 hole, I should actually get this one, but I will just mark that with a cross. Then 2 particle, 2 hole and 1 particle, 1 hole is something which does not need to be 0 because they differ only by 1 particle, 1 hole pair. They can. And then there's a 1 body operator, which brings us back to a 2 particle, 2 hole operator. So here I could put a non-zero. Here I obviously have a non-zero. Then here as well, I will have a non-zero. A 2 particle, 2 hole with itself is non-zero. But let's now move on to the other side. So what we have now is a case here where we have put up phi 0 here, and I'm just writing 1 particle, 1 hole, 2 particle, 2 hole, 3 particle, 3 hole, 4 particle, 4 hole, etc. So when I look at my 2 particle, 2 hole with a 3 particle, 3 hole, that is not necessarily equal to 0 because you have only 1 pair of states which can differ, which could differ. And then it doesn't need to be 0 here either, but then it will be 0 for all the remaining ones. Similarly, if I now take my free particle free hole, that can actually link up to a 5 particle 5 hole, but then the rest will be 0. And this will continue. So this one can link up with that one. It can link up with a 6 particle 6 hole, but then the rest is zeros. Now, if I then rewrite this more like a matrix structure, let us rewrite everything here. And in this specific case, what I'm going to do now is just to write the blocks, 0 particle, 0 hole, 1 particle, 1 hole, 2 particle, 2 hole, 3 particle, 3 hole, 4 particle, 4 hole, and this goes all the way up to n particle, n holes. And then I have 0 particle, 0 hole here, 1 particle, 1 hole. So these are states which I'm calculating integrals of, and then 3 particle, 3 hole, 4 particle, 4 hole, and then all the way down to n particle, n hole. Now, if I now only have a two-body operator, and I use the Condon-Slater rules, I'm going to mark all the guys which are non-zero with crosses. So I have a two-body interaction, so these are non-zero, and all these guys are 0. This is non-zero, 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 non-zero. This is 0 and 0. So here we have all zeros. But then when I look at the 1 particle, 1 hole, I can link up to a 3 particle, 3 hole, but not, since I have only a two-body operator, to that one. Similarly, here I can go up to 4 particle, 4 hole, and then the rest are zeros. Here I can now link with the 1 particle, 1 hole, 4 particle, 4 hole, 5 particle, 4 hole, and the rest are zeros. So you start seeing a pattern here. So this is going to be 0, this is non-zero. So if I now look at this, everything which is above or below these lines are 0. So what we are doing here is actually to construct a Hamiltonian matrix with a Slater determinant lambda, with a Hamiltonian, and a new Slater determinant delta. And you see that this is a sparse matrix. The way we have organized things now, because if I had organized my Slater determinants differently, I would not be able to set up these specific blocks, because this kind of blocks allows us now to say that, okay, this is the link between the ground state and 1 particle, 1 hole excitations, 2 particle, 2 hole, 3 particle, 3 hole, etc. And due to the fact that we have only a two-body operator at most, or perhaps a three-body operator, then there are many, many of these matrix elements which become 0, simply due to the fact that we have an orthogonal single particle basis. This is extremely handy. So this way of organizing it gives us now a kind of band diagonal matrix. It's a sparse matrix. It's also so that if you look at the expectation values which we are looking at, or the transition probabilities, we can then easily set them up, because we know that if we have this specific type of elements we are looking after, then we have an analytical expression for those matrix elements. And in case we have tabulated these integrals, the only thing you need then is to look up a table where you have listed the value of these integrals. So these are many body states. Keep that in mind, eh? These are genuine many body states, but then you're breaking them down into integrals which involve just two body states. Okay? So that means that the kind of Hamiltonian matrix, so I'm anticipating a little bit the structure of the Hamiltonian matrix. So let us now write down the formal equations for full configuration interaction theory. Because at the end, what we are going to diagonalize is a matrix which looks like this. This way of understanding then is also going to link us to different many-body methods. So when we do Hartree-Fock theory, because you know that when you want to diagonalize such a matrix like this one, you're going to perform a series of unitary transformations so that the matrix becomes diagonal at the end. And then you would just read off the eigenvalues immediately. When you do this, it's a set of operations. So ideally, so let's just bring this up. Suppose you have an eigenvalue problem, and let's just look at the basic mathematics of an eigenvalue problem. So suppose I have a matrix A, and I have a vector X. This is now given by the eigenvalue times the vector X. Now, the way we typically want to do these calculations is to find a transformation of A, which now brings us into a diagonal matrix. So ideally, we would like to have, if these are orthogonal matrices, that there is some ideal orthogonal matrix or unitary matrix, which makes A diagonal. This is the essence behind the diagonalization algorithm. So U is an orthogonal matrix, which means that U transpose times U is equal to the identity matrix, and then the inverse of U is equal to the transpose of U. It means also that every column vector of U is an orthogonal vector. Now, when you do this, what happens then? Suppose now that I take and multiply U with A and X. Now, lambda is a constant, so this is the same as U times X. I can now insert I here, which is the same as U transpose times U. This is, by the way, also the same as U times A times U of t. You can show that. If I insert that one there, then I'm going to have U of A times U of t, and I'm going to isolate it like this. And then I have U of X equal to lambda times U of X. So what you see now is that the eigenvectors change. But this could now become equal to a diagonal matrix times D. The eigenvectors change, but the eigenvalues are conserved. And the matrix is diagonal, and I can read off these elements immediately. Now, unfortunately for us, if you're beyond the 2x2 matrix, there is no unique U which you can write down analytically, except for some special matrices. So that means that this operation here, the standard recipe, is that you perform a series of such operations so that you would have a UM of U of M minus 1 down to U of 1. And this is acting on this one. And then you have a U1 transpose. And you do this many, many times up to U of M minus 1 and a U of M here. Now, what you could find, and this is the analogy between the full configuration interaction and Hartree-Fock theory. So Hartree-Fock theory, and this is where we will stop today, Hartree-Fock theory is equivalent, I should write is equivalent, because you won't get exactly the same result, but it is equivalent to setting these integrals f of a, which is equal to the block between phi 0 of h with phi I a, and we are setting these to 0. So it's equivalent to setting that one, which means mathematically that there should correspond that there is a transformation U which does this for us. So as I said, there are many, many steps, and you could now think of the first step in the machinery here as a step where you zero out just some blocks of the elements. So think now that you have found a transformation U which zeroes out this one and that one, and that's it. The hope then, since you then are performing an orthogonal transformation, then these matrix elements will be a little bit different. And hopefully that one is a better representation of the ground state. Also, by changing the basis, the hope then is that the coupling between the new one here and the other ones, other blocks, is smaller. So that perhaps this becomes a better solution if you now transform away these ones. So you can think of Hartree-Fock as an orthogonal/unitary transformation of the full Hamiltonian matrix, which we are going to discuss in more detail next week. So I wanted to use this as a kind of way to build up the intuition of how we use this basis to set up a Hamiltonian matrix, which we afterwards are going to diagonalize. And we will use this picture to actually motivate other many-body methods, which then will just be approximations to the full problem. And the full problem is us being able to diagonalize this matrix, which in general is not possible because we have too many degrees of freedom. So the state of the art nowadays, computationally, is matrices of the dimension of 10 to the power of 10 times 10 to the power of 10. And you would use iterative methods to solve these eigenvalue problems because you cannot diagonalize exactly a 10 to the power of 10 times 10 to the power of 10 matrix. But in principle, if you can solve this problem, you have solved the problem. And the rest of the course now, after we're done with FCI, is actually to interpret approximations in terms of unitary transformations, which we are going to make on that matrix. Does that help a little bit to make a kind of a picture of what is going on mathematically? Yeah.
So when we do this, are we going pure numerical, or are we trying to keep working symbolically?
There are very few. The exercises you will get are cases which you can solve numerically. So these are small cases, but normally you have to solve numerically. And there are very few matrices where you can find eigenvalues analytically of. There are only some special matrices where you can actually, if you think of a third order polynomial, sometimes you can find the roots immediately, but you have something which is called the Abel-Ruffini impossibility theorem, which says that beyond a fifth order polynomial, which is then the characteristic polynomial of a 5 by 5 matrix, you cannot find analytical solutions in terms of rational numbers, but you can still solve it. So not finding a solution in terms of rational numbers means that you cannot find an analytical solution. That does not mean that you cannot solve the problem. You can solve them to numerical precision.
What was that theorem called? What was that theorem called?
Abel-Ruffini. Abel-Ruffini. So actually Abel, who died at the age, what was it, 25, 26, suffered from, I think he suffered from pneumonia. He died pretty early in the 18th century. He did extremely many groundbreaking contributions to mathematics. You have a billion group theories, and it's like these people like Gauss and other people. It's so intimidating because you see their names everywhere. And you have the feeling that they did everything right. Okay, I'm going to stop the recording here.